visualization of real-time GPS data. My name is Megan Kostick. I'm the team lead. Wendy Stockwell is our requirements analyst, and she is unable to attend tonight.
I'm Sergio Bugis, and I'm a database specialist.
I'm Kyle Kincaid, and I'm the software architect.
I'm Maggie Stoll, quality assurance lead.
Our client for this project is Tim Melbourne and his team. Tim is an associate professor here at Central Washington University, and he is also the director of PANGA. Our advisor is Dr. Razvan Randonier, a computer science professor here in the department. Just to show you guys what we'll be discussing this evening, we'll give you an overview of the project, going to talk about our database and give a short demo of that, along with a demo of our graphing utility that is in our application. And then we will discuss the quality assurance and testing we've completed so far, and then conclude and answer any questions you may have. To refresh you guys on our project, we are working under the United States Geological Survey, known as the USGS. They're an organization that employs experts in both the earth and life science fields to monitor and better understand the earth. Their mission is to learn more about the earth we live on, and through that understanding, create a better quality of life for us on Earth. PANGA is the Pacific Northwest Geodetic Array. They are working under the USGS. They're a research team here at Central Washington University, and they monitor and analyze data from over 300 GPS monitoring stations placed throughout the Cascadia subduction zone. They have a special interest in earthquake prediction and seismology. The Cascadia subduction zone stretches from Canada down through California. It's a zone that's very high risk for earthquakes, and these sensors have been placed throughout that zone to record shifts in the Earth's plates at those points. And from this data, they can predict earthquakes. The problem that our client has is that PANGA is receiving all this real-time data into their huge server here in the geology lab. And this data comes in just as raw data. They can view it, but it takes kind of expert knowledge to interpret it. And right now it's geared towards improving survey techniques, where they want to extract this data in order to use it for earthquake prediction instead. Currently there is no software tool available for them to view this data visually, and that is one of the problems they're having and have asked us to solve. And we've come up with a solution, working with them, to develop a real-time GPS visualization application. And this application will have various features to view the data, and it will be an independent desktop application. And they also need an application that's open for extension, because this data can provide benefits of earthquake prediction and data mining possibilities. I'll now transfer it over to Kyle, who's going to talk about some of the requirements our clients have set forth.
Okay, so our client has given us a set of functional and non-functional requirements. Some of the functional requirements include a site list, so that the user can specifically search for sites or stations, a map view, so that the user can visualize stations and their location, a graph view to visually represent the data that is streaming in, and a saving function to save the data that is currently being viewed, as well as tabs for space for future extension. Some of the non-functional requirements include making this application a Java desktop application. This allows the application to be cross-platform, and this is a requirement set forth by the USGS. Also, maintaining a real-time data stream and maintaining a connection between the database and the server. And now Megan will talk about what we have done so far.
All right, so last quarter, just to recap, we finished our first iteration, dividing last quarter and this quarter, and we had a GUI that was approved by our client with an appropriate layout and what they wanted. And that included a functional map view with the stations plotted, and you were able to view the streams for each station, along with a searchable site list. Also, the database schema was approved by our client, population, starting this iteration. To break down the sprints that we were planning on having this quarter, we will have 3 sprints. Today marks the conclusion of our first sprint, which was to get a graph view fully approved by our clients and begin implementation on that within the GUI itself. Also to have database connectivity with their server, which has been completed and data is streaming in. And also just to perform acceptance testing in this iteration, so everything is laid out and set up for our future sprints. For sprint 2, we want a full integration of the interface with the graph view, map view, and the station lists. And the graph will also interact with our database, streaming in the live data and plotting points, and all functionality will be present. We also will be performing our unit testing on the pieces once the functionality is there, along with acceptance testing and integration testing between the multiple pieces. Our final sprint is at the end of this quarter, and it's just the system polish, making sure everything runs correctly on our clients' computers, and that we perform all the correct stress testing and acceptance testing and make sure we have a product that meets their satisfaction. And now Sergio is going to discuss our database.
So as Megan mentioned, one of the main tasks that we set out to complete for our first sprint was to establish a connection between our client's server and our database. To do this, we used an aggregator that our client provided for us to collect data for each stream or station. The aggregator takes in a stream name, a queue name, and a last query time. The stream name is used by the aggregator to tell it what station we would like to collect data for. The queue name is a determinant that the aggregator uses for roughly how many data points we'll get back in a given time window. And the last query time tells the aggregator when we last created for our data, and it uses this information to only return points that are new in that time. This is beneficial to us as it keeps us from having to handle multiple copies of the same data. So the data that we get back from the aggregator is in the form of a JSON string. We use the JSON sample library to decode this string and extract the data. Since we haven't completed the integration of our data streaming with our user interface, we put together a small application to demonstrate this real-time streaming plan. For the purpose of this demonstration, we hard-coded in a 5-minute queue, and so the only thing we'll pass into it here is going to be a stream name. And since we're using this 5-minute queue, when we first query the aggregator, it's going to give us back the data points for the past 5 minutes that the aggregator has stored. So as you can see here, this is the first initial data that it has backed up. And then as the aggregator gets new points, it'll push it through to us, and then we receive them as they're coming in. And the time gap between each of these points is really dependent upon what stream we're using, what stream name and what query name we're using, or the queue name that we're using. And we also have the ability to open multiple streams at once. Since each stream is open in its own thread, we can monitor the data off of multiple streams at once. So here you can see that there's a contrast between a station that opens up every 5 seconds and one that opens every 15 seconds. Yeah. One of these stations is giving us a new point about every 5 seconds, while the other one is giving us points every 15 seconds. And that concludes this presentation of the streaming data for the demonstration side. Okay. So as I mentioned, each one of these streams is open in its own thread, and each thread contains a stream name and a queue name, which it uses to create an aggregator and get data that corresponds to those 2 fields. That data is then inserted into the database using or through the Java Database Connectivity API. And the image on the screen is a screenshot of a GUI that we use to ensure that the data that we're inserting into our database is valid data and is going to the proper location. Currently, we're receiving the longitude and latitude position along with the timestamp for when that position was recorded. However, our client would like us to graph the changing position as a north-east and vertical component, so they're working on providing us with an enhanced aggregator that will give us the actual north, east, and vertical position of the station. And this will make it easier for us to actually graph that on our user interface. However, we'll still be using the longitude and latitude aggregator to plot the initial position of the station on our map, which is also part of the user interface. The In addition to that, the client is working on providing us with the sigmas or the error in the points or the position that they are recording and passing on to us. And this is some information that will most likely be used in future extensions of the graph view to our application. And I'll let Hal speak more about the graph view.
All right, so now that we can get the data, now we want to graph it. And we've looked at many open source real-time graphing libraries, notably ptplot, jfreechart, and jchart2d. But in the end, we decided to go with jchart2d because of it's more focused on real-time graphing. And we currently have the graph in our interface, and it's functioning right now. We are currently configuring it to meet the client's needs, and when it is done and fully configured, then we will begin streaming live data. So now we'll show that to you. All right, so this still looks quite similar to the last presentation. It still has a site list and a map, but on the right you can see the empty graphs. And to populate the graphs, we can just choose a station from the map. So once we choose a station from the map, we can select one of the available streams, and now you can see that it's graphing data. Currently we're using test data just because we don't have that fully implemented. And also below the graphs, you can see that there's no longer a configuration menu. We've been asked to move this to each individual graph, so we now have a gear icon or a gear button that the user can click, and this should bring up a configuration menu. And this allows us to configure each graph individually, whereas before it was slightly confusing what the user would have been configuring. So you can select the time window that you would like to view on the graph, and you can select the sets of data that you would like to view on the graph. Currently this is just visual though. We still have a few more changes to the graph, and yeah, so then we can implement that. And we can also remove stations from the graphs by selecting the X on the top right. And yeah. We're working on extending this open source material so that we can actually fine-tune it to the specific needs of the client though. So we still have to do that. And so that's the end of our demo. And now Rosie will talk about quality assurance and testing.
We began this project with two main goals. The first goal, of course, was to provide our client with software that meets all of the requirements they set for us. Complementary to this is our second main goal, which is to have full accountability within our team. To us, this means that each team member must be confident enough in their knowledge of the project that they could fill in case of the temporary loss of a team member. At this point, our software does meet all of the requirements that have been set for us, and our team works together flawlessly with a very positive atmosphere. Some of our strategies for achieving this success is to allow no fewer than 2 team members to work on our project at any time. We also meet several times a week to discuss our progress and address any concerns, and we focus on assigning tasks according to each team member's strengths. Chief among our standards at the moment are, with regards to writing our comments, we want them to be compatible with the Java docs tool. So we are currently filling our code with what looks like multi-line comments, but are actually comments that can be used to generate external documentation about our code. And we're aiming towards 100% code coverage. Hopefully we'll be able to achieve that next sprint when we begin rigorous unit testing. At the beginning of each week, we have a meeting where we decide what we're going to be developing for the current week and begin testing what we completed the previous week. So far, this has yielded no major errors, but it has yielded some kind of hilarious small errors. One of my favorites is that we sometimes have floating text in the middle of the graph that is backwards. And we're working on fixing that, but thankfully that's the largest error we've encountered so far. We also are maintaining our focus on constant communication with our client via email or in person. We demonstrate our progress to our client weekly so that we have a little bit of informal acceptance testing, and our client and his team can view our progress, give us feedback, and request any adjustments to the current At the beginning of Sprint 2, along with the unit testing, we will be conducting formal acceptance testing, where both our team and our client's team will fill out the RISC user acceptance forms. And we will compare our results with theirs to ensure that everything's running smoothly for the entire project instead of the individual features we've been testing thus far. We will now go back to Megan to conclude the presentation.
All right, so as you've seen, we finished our Sprint 1 completely to our client's standards, and now we'll be continuing on to our final 2 sprints to finish our application and be able to deliver it to our client. So far, our development plan has worked very well among the team and with our clients as well. It's really nice to have that feedback and be able to, change to their needs and requirements. And we think by staying focused, we're going to be able to have this application ready for them by the end of this quarter. We thank you all for listening, and we'll now open the floor for any questions you may have.
So what are these called? Aggregates or aggregations?
Aggregators?
Yeah, aggregators. What exactly do those do?
Okay, so the data that we're using is from our client's database, or a big server that they have. They're getting, they're recording the data that's coming off the actual GPS station and storing it in a really big server that they have. And then from there, they already have a system that they use to get that data onto an aggregator that they have for us. And basically, they pull their own data out of the big server and pass us the information that we need.
So it's cleaning up the database for you. Is that what it's doing, or is it? I'm not sure what exactly it's doing.
So like they have they have a big database that they have with all the information in it, but it's kind of like raw data. So then this aggregator is kind of like a translator, like something that we use to get data from there into our smaller database.
That makes sense.
So what are you actually saving in your database?
We're saving the positions that are those same positions, but a lot less fewer of them, and in a more, like a temporary. We only store 24 hours worth of positions for each stream.
And you're saving continuously, or you're getting rid of it after a while? Or?
Yeah, we get rid of it after the 24-hour mark. Or data that's called 24 hours is deleted, so it's kind of constantly being refreshed.
Yeah, so you're not actually saving the data. That's a different project.
Yeah, they have their own database that's saving other stuff.
The client didn't want to require that they have a server connection readily available on their machine
Oh, I see.
and have like that huge hard-coded database. And so it's a more temporary.
It's kind of just to give our graphs somewhere to grab our data from.